In this lesson, we're going to use our knowledge of formulas in the coordinate plane together with our knowledge about triangles to prove some facts about triangles. Just as a little reminder, up at the top of the page are 3 formulas that we've used quite extensively so far this year. You know at this point distance formula, slope formula, and midpoint formula. So I'm going to jump right over those and get into this whole notion of developing a coordinate proof. The steps that you're going to follow are there in that box, and I know you can all read, so I'm going to go ahead and jump right into this and get down to business. Step 1 is to go ahead and draw and label the graph. So in this very first example, we're given the triangle ABC with the following coordinates. So I'm going to begin by plotting those points and going ahead and drawing the triangle so I can get a good picture of exactly what it is that I'm working with and looking at in this particular example. So there's the triangle that we've been given to work with. Our goal, our mission, is to prove a couple different things about this triangle. The first thing that we want to prove about this triangle or show about this triangle is that it's isosceles. So in order to do this, you have to consider the question, what is it about a triangle that makes it isosceles? What properties does it need to have? What characteristics does it need to fulfill if it wants to be an isosceles triangle? And this is a question that most of you too know the answer to. You know that anytime a triangle has 2 congruent sides or 2 equal sides, the triangle is going to be isosceles. So that's the first qualification that we need to show that this triangle meets. The second thing that we need to demonstrate about this triangle is that it's a right triangle. And when I ask that same question, what qualification does it need to have? What needs to happen in order for this triangle to be a right triangle? The answer that most of you are going to come up with or reply to me is that it has to have a right angle. And I'm fully in agreement. If we could show that this triangle has a right angle, we'd be in good shape, and we know that our triangle's a right triangle. There's one other thing that might not jump quite so quickly to mind with respect to the fact that it could be a right triangle, and that is the use of the Pythagorean Theorem. Anytime the sides of a triangle fulfill the Pythagorean Theorem or make the Pythagorean Theorem a true statement, the triangle is said to be a right triangle. So we can also use a squared plus b squared equals c squared. And the reason that I bring that up is because I'm already going to use the distance formula to find that 2 or to show that 2 of the sides are congruent. I may as well use distance formula one more time and then plug into that formula. It might be a little bit more efficient than going and finding a whole new pair of segments and doing the slopes on the segments and using the negative reciprocal slopes to establish the right angle and so on and so forth. But either one of those strategies would be a really good strategy for proving this triangle is both an isosceles triangle and a right triangle. It's really a matter of personal preference. I'm going to do distance formula 3 times and then show the lengths of my sides satisfy the Pythagorean theorem. All right, so with that said, because I'm going to use the distance formula, I need to write it down on my paper. And what I want to do is go ahead and find the lengths of all 3 sides of the triangle. So I want to find the length of side AB, or in other words, the distance between points A and B. I'm going to clearly indicate on my paper exactly which segments I'm finding distance or length for. So distance between A and B is the square root of 4 subtract 5 quantity squared plus -1 subtract 6 quantity squared. And I'm going to take a minute and put this all into my calculator. You should do the same too. If you need to go ahead and pause the video, go ahead and pause the video so you can get your calculator out. But you want to be doing these computations with me at home while I'm doing them here in the video, just to make sure that you know how to use your calculator and how to perform the calculations. So I ended up with square root of 50. And this is something that's going to feel odd and feel strange to you. When doing a coordinate proof, we are not going to simplify the radical. It wouldn't be incorrect to simplify it, but actually leaving the radical as it is, it's going to make it slightly easier to work with when we go and do some further calculations or computations with that answer. So for the time being, I'm just going to go ahead and leave AB as the square root of 50. And I'm going to move on to my next side and go find the length of segment BC. And again, as I substitute these values into my calculator, you want to make sure you're doing the same thing at home, just to double check me and make sure that you're on board with performing these calculations and computations. So I end up with square root of 25, which again I could simplify to 5, but I'm going to leave that in unsimplified form. And then the last side that I need to find the length for is side AC. So this one too came out to be square root of 25. So at this point, I know that this triangle is isosceles due to the fact that it has two sides of equal length or equal measure. So my last step here is to now explain all these wonderful calculations and computations that I've shown. Why does doing the distance formula establish or prove the fact that this triangle has to be isosceles? So triangle ABC is isosceles. And the reason I know it's isosceles is because it has two congruent sides, or it has two sides of equal length, however you want to say that. To show that it is a right triangle, I'm going to substitute the lengths of its sides into the Pythagorean theorem and demonstrate that they work, or they satisfy the Pythagorean theorem. When doing this, you do need to be very careful of one thing. In a right triangle, the hypotenuse, opposite the right angle, is always the longest side of the triangle. So when I go to substitute these into the Pythagorean theorem, I just want to put out there this gentle reminder that in the Pythagorean theorem, A and B represent the two legs of the triangle, whereas C represents the hypotenuse. So when substituting into the Pythagorean theorem, you need to make sure that you use your largest length for your C value. So my square root of 25 goes in here for A and B. Square root of 50 goes in here for C. So now I need to go ahead and plug that into my calculator. The square root of 25 squared, or in other words 5 if you're more comfortable with working with that. And that's going to be equal to 50 on the left side of my equation. And on the right side, when I square the square root of 50, I also end up with 50. So the lengths of these sides do indeed satisfy the Pythagorean theorem, meaning that the triangle is a right triangle. So triangle ABC is a right triangle because its side lengths satisfy the Pythagorean theorem. And again, if you were thinking to yourself it might be a little more fun to work with slope and use slope to establish perpendicular lines and therefore a right angle, that would get the job done just as effectively. As always, thank you for the gift of your time in viewing the video and learning the material. I do want you to take a few minutes and reflect upon what you've seen and write down on your paper the key ideas, the important takeaways from the video that you saw here today.